Okay, 3.3 is optimization problems. So what is optimization? This is the process of optimizing a situation. So it's just like realizing the best possible outcome subject to like a set of restrictions. So basically what we're going to do is we're going to solve the maximum or minimum. They're going to be real life problems and it's going to give us restrictions. So such as minimizing the cost of making tables and chairs, given a certain amount of material or given like a certain amount of money, for example. Okay, the domain is usually restricted on such things as time or amount of material again or cost. Okay, so let's do example 1. And we touched on this in grade 9 on the optimization unit. It's usually the last unit before the exam, but we're going to do it in like a calculus way this time. Okay, so a farmer has 800 meters of fencing and wishes to enclose a rectangular field. Okay, but one side of the field is against a road, so he only actually has to fence 3 sides because this one's already fenced right here. Okay, the farmer wants to enclose the maximum possible area to use all the fencing. Okay, so we know that the perimeter is going to be 800. How does a farmer determine the dimensions to achieve this goal? Okay, so let's call the width x, and we know the length is going to be like 800. Subtract that 2x. We don't know what that's going to be though, but we can use the area as x times that 800 minus 2x. Okay, so we want to know, how does the farmer determine the dimensions to achieve this goal? So he wants to enclose the maximum area. So we go ahead and we take area and we find the derivative. I'm lazy. This is a really, really easy expansion. So I'm going to do 800x minus 2x squared. Now I'm going to find the derivative opposed to using product rule. Okay, so here's our derivative. Okay, so let's go ahead and set the area equal to 0, or the derivative of the area equal to 0. So we have 800 equals 4x. We divide both sides by 4. We get x equals 200. Okay, now we're going to test x equals 200, but then also we have to use common sense to know what the limitations are here. Okay, so take a look at this. We have 2 x's. The area, the perimeter, the x, since the x's are divvied up between like the left-hand side and the right-hand side, the maximum that the x can be is just less than 400. So it's going to be between 0 and 400. But it's not going to include 400 because at 400 we have 400, 400, and 0. We have like this. But 0 times 400 gives us an area of 0, which doesn't actually give us a rectangle. So that doesn't work. So it cannot, we can't have a width or a length of 0 for a rectangle, because then the area will be 0, and then the rectangle will actually not even exist. So these are the three numbers that we're going to test. Okay, so let's test A at 0. Let's test A at 200. And let's test A at 400. Okay, from the original. What do we get? Okay, when we sub in 0, we get 0. When we sub in 200, we get 80,000. And we sub in 400, again, we get 0. Okay, just like what I told you, there's not going to be any area if there's no length or no width. Okay, so those are just completely unrealistic. So the maximum area is 80,000 with length of 800 minus 2x is 400, and width of 200 meters. and that's meters squared. Okay, this one's a little bit more complex. So a piece of cardboard that is 60 by 30 is being used to make a rectangular box with an open top. So if you ever get like a box that like a case of soda comes in, what happens is when you break it down, it looks something like this. Okay, where these four corners will be cut out, they'll all be X in length. Okay, but those four corners are cut out. So the actual length is going to be 60. Okay, and then the width is going to be 30. But if you think about it, this length in here is going to be 60 minus 2x, and this width in here is going to be 30 minus 2x. Okay, and then the height's going to be x. So we want to determine the largest volume. So you see the word largest, you think maximum. You see volume. Let's find an equation for volume of this. So we're going to have, like, when this box is like propped up, we're going to have 60 minus 2x, 30 minus 2x, and then we're going to have that multiplied by x. I'll throw that right in the front. Okay, I'm lazy. I'm going to expand these. Okay, 60 times 30, 1800. 60 times negative 2 is negative 120x. Negative 2 times 30 is negative 60x. And then plus 4x squared. I'm going to collect these, put this in front, and expand the x all in one shot. 4x cubed, we get negative 120 minus 60. We get negative 180 x squared. And then plus 1800. Okay, so here's the equation for volume. Now let's find the derivative for volume. Okay, so it's volume with respect to x. Okay, we get 12x squared minus 360x. Okay, that's the derivative for volume. Oh, sorry, this had the x on it. Okay, this had the x on it, so it's plus 1800. My mistake. Okay, so now we have to figure out when does the accelerate or the velocity of the volume equal 0. Okay, let's pull out this 12. We're left with x squared minus 30x plus 150. Okay, 1 negative 30, 150. This is an ugly one. You have to sub this into quadratic formula, and you're going to get left with x equals approximately 23.7, and you're going to get x equals 6.3. So go ahead and do that. I'm not going to do that work. So now what we have to do is we have to determine the interval. Okay, when we're dealing with volume, all of x, 60 minus 2x, and 30 minus 2x have to be positive. So this right here is going to be our restriction. Our x is going to have to be between 0 and 15 in order to keep this positive. Okay, if you need to actually do the work, 30 has to be greater than 2x, divide that by 2. Okay, x has to be less than 15. Okay, so now what we're going to do is we are going to solve for v at 0, v at 6.3, and v at 15. Okay, remember 23.7 is not in the domain. So when we check these numbers, we indeed get, okay, we get 5195.988 for this. This will give us a volume of 0. This will give us a volume of 0. So we have the dimensions. I'll finish this on the next video.